Exponential functions are those with variable exponents. There is a distinct pattern when taking their derivative. Check out the examples here in differential calculus. The main pattern for the derivative of the exponential function is derived from the derivative of a raised to u with respect to x. And this is taken as a raised to u times ln of a multiplied by du all over dx. This is the main formula, although there can also be times that instead of a variable a, the natural number e can be involved. In such a case, the same pattern is still used, so d all over dx of e raised to u is e raised to u times ln of e multiplied by du all over dx. Note that ln of e is 1, so the derivative is simply e raised to u times du all over dx. Check out some examples for the differentiation of the exponential functions starting with y is equal to e raised to negative 3x. Since the natural number e is involved, then the pattern to use is the shorter one. Take u as the exponent of e, and that is negative 3x. U prime is then negative 3 times dx all over dx, which is taken as 1, so u prime is negative 3. Place the solved values in y prime, that is e raised to negative 3x times negative 3, or y prime is equal to negative 3 times e raised to negative 3x. The second example has the equation y is equal to e raised to secant t. Just the same as the previously solved, u is secant of t, and u prime is secant t tangent t times dt all over dt, which is again 1. U prime is simplified as secant t tangent t. Thus, y prime is then solved as e raised to secant t times secant t tangent t. The next example to differentiate is y is equal to x times e raised to negative 2x. With two terms in the expression, we use product rule. So y prime is x times the derivative of the second term, e raised to negative 2x, plus the second term multiplied by the derivative of the first term x. The last part of the second term is 1, but the derivative in the first term will employ exponential function, so we needed to find u and its prime. U is negative 2x, and u prime is negative 2 times dx all over dx, simplified as 1, so u prime is negative 2. Plug these values into the y prime equation to have x times e raised to negative 2x times negative 2 plus e raised to negative 2x. Arrange the terms to finally have y prime as negative 2x times e raised to negative 2x plus e raised to negative 2x. Example 4 has the function y is equal to ln of the quantity 5 minus e raised to 4x. The derivative of ln is u prime all over u, where u is the binomial 5 minus e raised to 4x. Its prime is the derivative of 5 minus the derivative of e raised to 4x. The derivative of a constant is 0, but the second term requires the pattern for the exponential function. Now, we needed to find the second u, and to differentiate this from the first u earlier, we denote the second u as u asterisk, which is 4x. Its prime is 4 times dx all over dx, which is reduced as 4. So u prime is 0 minus e raised to 4x times 4, or take u prime as negative 4 times e raised to 4x. Finally, y prime is negative 4 times e raised to 4x all over 5 minus e raised to 4x. The next example has r is equal to e raised to negative theta cosine 2 theta. With two terms involved, we use product rule. We start with y prime as e raised to negative theta times the derivative of cosine 2 theta plus cosine 2 theta times the derivative of e raised to negative theta. The derivative of cosine 2 theta is negative sine 2 theta times further derivative of 2 theta. And the derivative of e raised to negative theta is itself times the derivative of the exponent negative theta. This is reduced to negative 1. Similar with d theta all over d theta in the succeeding first term, so y prime is then negative 2 times e raised to negative theta times sine of 2 theta minus e raised to negative theta multiplied by cosine 2 theta. Another example includes the function r is equal to 10 raised to 2t. Since there is 10 instead of e, we use the general formula for the derivative. Still the same, u is 2t, and u prime is 2 times dt all over dt, making the prime simply as 2. So r prime is 10 raised to 2t times ln of 10 times 2. We can actually compute for 2 times ln of 10, so r prime is finalized as 4.61 times 10 raised to 2t.